Started. Ooh. Rest of chapter 21. So this is where we left off talking about, right? We left off talking about fission and fusion, and tremendous amounts of energy are produced, right?
Yes.
Okay, so that's what we're going to talk about. So when we split an atom, we get lots of energy released, right? Okay, and so we can calculate that energy by saying E equals mc squared. So some matter is changed into energy. Now, before we haven't really needed to pay much attention to that because the amount of energy was minimal and the mass change was very, very small. It was negligible. But because we get so much energy from these nuclear reactions that we can detect the mass, and it is something that we need to take note of. So here we have this reaction. You have one uranium atom, one neutron coming in, splitting it, and we have two atoms, three neutrons, and lots of energy. So let's calculate how much the mass has changed. So we want to find the change in mass. How do you find change in mass? How do you find change? Remember how we do that? Change is what? Finest minus initial. So change in mass equals the mass final. What's another word for final when we're talking about products and reactants? Products. Okay, so mass of the products minus mass of the reactants, right? Okay, so let's look at the mass of each one of those. So here you have one uranium. Now, we're talking about one atom, so we're going to give it in units of AMU. Guys, remember AMU? Yeah, atomic mass unit. Okay, so that's AMU for that atom. This is the AMU for one neutron. That's what we're starting with. These are our reactants, so we add that together. Now, these calculations are not hard, but you really need to keep all those significant figures and digits. It's awfully, I know it's really long. So you spend most of your time just recording all those down. Okay, we don't want to round because we're talking about such small amounts that this is really significant. So you do need to keep all those. And then here's the barium and krypton and three. These are three neutrons. That's the weight of a neutron in AMU. So we add that up together. Okay, so here's the products added together. Here's the reactants added together. And we say products minus reactants. And you get a negative value, which is okay because we're talking about a change. It's okay to have a negative value for a change because that means, you know, we're decreasing. But it's not okay to have a negative mass when you're trying to weigh something on the balance. You can't have a negative mass there. But the change can be negative. So we can do that. So let's go ahead and subtract that, and we would get a negative 0.18489, and that is in AMU. Okay, so the units are in AMU per atom because this is what we're talking about, is that one atom. So AMU per atom. Now let's look at the E equals mc squared. All right, so m is mass, c is the speed of light. Now we have used the speed of light, what was 3? We said it's 3 times 10 to the power 8. Okay, when we're talking about such significant digits, we can't just use 3. That's not enough. That's too much rounding. So we're going to have to use a more accurate value for c. And so speed of light, c, is equal to, we're going to use this one, 2.9979 times 10 to the 8th meters per second. Now we're going to square that. So the units are going to be meters squared per second squared. And I want energy to be in joules. So 1 joule is a kilogram meter squared per second squared. So that means mass has to be in what units then? Kilograms. I'm over there in AMU. We got to get from AMU to kilograms, and then we can put it in here. All right, so let's think about how we're going to do that. Well, let's look at the periodic table. And do you remember those numbers underneath the symbols for the element, like carbon, those 12.011? Okay, what is that number? Grams in what? 1 mole. Do you also remember that it's an AMU of one atom? Okay, so if that's 12.011 AMU of an atom, it's also the same number, 12.011 grams per mole. So can't we take that to this as well? if this is a negative 0.18489 AMU per atom, then isn't it the same number in what? Grams per mole. Exactly, so we can do that. So this equals a negative 0.18489 grams per mole. Now, can you change grams to kilograms? Yeah. Oh, yeah, that's so easy. So we go ahead and change that to kilograms. We're dividing by 1,000. That's minus 1.8489 times 10 to the minus 4th kilograms per mole. That's what we're going to change that to. Now we're at kilograms. So you go from AMU per atom to grams per mole and then to kilograms per mole. Now we can put that in here. So we would put that number in for our kilograms, take our speed of light and square that, multiply those together, and we would get a negative 1.66168 times 10 to the 13th. Okay, that is a very large number. 10 to the 13th joules, and we still have our mole, so it's joules per mole. Okay, and it is a negative number. What does that mean, negative numbers? Does that mean energy is being released or added in? Released. That makes sense, right? Because you split it, energy was released. We had lots of energy. So yeah, it's negative. It's going to have to be negative. So that makes sense. All right, and that's our E equals mc squared calculations. We find the change in mass, watch our conversions to get to kilograms, put it into our E equals mc squared using a more accurate value of c, and that's how we do it. Easy, right? Okay, well, we're talking about the nucleus for these things, and when we have the mass of an atom, how do we get just the mass of the nucleus? Well, remember, the atom has the nucleus and all the electrons, so wouldn't we need to subtract out the electrons then, just to get the mass of the nucleus? Okay, so let's do that. The mass of the nucleus, here we go, for example, is going to be the mass of the atom minus. Okay, now how are we going to get the mass of the electrons? If we know the weight of an electron, I would need to multiply that by the number of electrons, right? In a neutral atom. Well, how are you going to determine that? How do you know? How do you know how many electrons? And looking at this symbol, how am I going to know how many electrons there are? Oh, it's the same number of protons, right? Because it's neutral. So if I have 92 as my atomic number, the number of protons, does that mean I have 92 electrons? Yes. Okay, so you take the mass of the atom minus 92 of those times the weight of the electron. Does that make sense? Okay, so we subtract that out, and that is the mass of the nucleus. So we kind of need to pay attention if we're talking about the mass of an atom or the mass of a nucleus here with these. Okay, make sense? All right, so here we go. We split the atom and we got energy out. It was negative. Well, remember, the nucleus is held together by, all those nucleons are held together by that strong force. Well, what would it take to separate all those nucleons? It's going to take a lot of energy. Yeah, it is going to take a lot of energy, isn't it? Okay, so all those nucleons are held together by the strong force. So I'm going to have to put energy in, aren't I, to separate those out. Okay, and the bigger the energy going in, the more stable the nucleus is, isn't it? All right, so we're talking about energy in. So we're going to give that a different name because that's different from the energy coming out. This is the energy it takes to separate those nucleons. So we're just going to give it a different name. We're going to call it the binding energy. Okay, so it's going to be a binding energy. And we're also going to have a change in mass again, but we're going to give it a special name as well because we're talking about separating all the nucleons. So we're going to call that the mass defect. So mass defect is the change in mass specifically referring to separating all the nucleons. And then binding energy is that energy. Now let's talk about the units here. So this is the mass defect, and that's going to be per nucleus here. So you might want to make note of that. Mass defect, okay, in AMU per an atom, we could say. Okay, so that's a mass defect per atom. So you might want to write these units down, make sure you've got that. And this is the binding energy in joules per atom, because that's different between joules per mole or joules per nucleon. So we need to be clear. So let's specify that very clearly. So make sure you write that in your notes. That's going to be joules per atom. And then this one is going to be joules per nucleon, and here it's labeled as joules per nucleon. Okay? All right, so let's see. How are we going to get that binding energy? And we can talk about it as energy in joules per atom, or we can talk about it in joules per nucleon. So, mass defect. So let's talk about that. All right, let's write our equation down here of what we're doing. We are taking our nucleus and we are adding energy, right? Aren't we taking our nucleus and adding energy? So we would say nucleus plus, and what did we call that special energy we said? It was called what? Binding energy. Okay, so this is going to be binding energy. And it's going to be on this side, the reactant side, gives us all our separated nucleons. There you go. So nucleus plus binding energy gives us the nucleons. Now, we want the change in mass. So we said, oh, that was products minus reactants. Okay, so what's our product here? Nucleons. All right, so then my mass defect, remember we call this the mass defect, the change in mass. So let's write that down. Mass defect is equal to the mass of the nucleons minus the mass of the nucleus. That's what it is, nucleons. So let's just work this first example with helium. Let's do that example here, the first one. And I need the mass of the nucleons. Well, there's the mass of the nucleus. Okay, so that's given to us. That's the 4.00150. So that's the mass of the nucleus. But I need the mass of the nucleons. Now, how am I going to get the mass of the nucleons if it was not given to us? Okay, well, let's say this is not given to us at all, and we need to figure that out. Well, okay, but we don't have them. We don't have any of these other numbers. We don't have any of these numbers, and we're going to figure out what all these numbers are. So then that's the question: is how am I going to get the mass of the nucleon? So I can get the mass defect. So I can get the binding energy. Okay. So let's just say we don't have any of these numbers. The mass of the nucleons. All right. Well, first I have to know how many nucleons there are, right? And you remember we said there are protons and neutrons. Well, how am I going to know the number of protons?
Periodic table.
Yeah, atomic number, right? Periodic table, sure. Okay, well, how about the number of neutrons then? Okay, mass number. Yeah, can I take the mass number minus the number of protons, right? Okay, so we will be given the mass of the protons and we will be given the mass of the neutrons. It's up to us to figure out what is the mass of the nucleons. All right, so the mass of the nucleons. Well, we said for this one we had 2 protons, so the mass of the nucleons would be 2 protons, and each proton weighs 1.00728 plus 2 of the neutrons at 1.00866. And it is an AMU, exactly. It is an AMU. Okay, so if we add that up together, then that gives us our mass of the nucleons in AMU. Okay, so this is AMU. All right, does everybody see how we got the mass of the nucleons? You see how we did that? Okay, so let's take a look at this next example. Iron 56, and there are 26 protons. So to find the mass of the nucleons, I would say what? 26, what? Protons, 26 times the protons, and then how many neutrons though? 30 neutrons, and I'd add those together. And when I do, that gives me that mass of the nucleons. So does everybody can get the mass of the nucleons? Yeah, so easy, you know, what's a little adding, subtracting, right? Okay, so this is the mass of the nucleons, and that's what we have. It's the 4.03188. I'm going to take the mass of the nucleons that we just figured out minus the mass of the nucleus. Okay, and that's going to give me my mass defect, right? Isn't that what we said? Mass of the nucleons minus the mass of the nucleus. So let's do that. Put that number in for the nucleons. 4.03188 minus 4.00150. And that is my mass defect. And the mass defect is 0.03038 AMU per atom. But don't we have to change those units? Okay, we got to change it first to what? Grams per mole, and then we change that to kilograms per mole. Exactly. So we do that. We would get 3.038 times 10 to the minus fifth kilograms per mole. That's what we would get for the mass. And I multiply that by my C, which is the 2.9979 times 10 to the 8th meters per second. Don't forget to square that number. Don't forget to square that number. And that's going to give me my energy is 2.7304 times 10 to the 12th joules per, now remember, this is going to come out to be joules per what? Per mole, exactly. It comes out to be joules per mole. It's a positive number. Makes sense, because don't we have to put energy in? Yeah, so it should be positive. All right, so that's my energy in joules per mole. That's called the binding energy. But I want that in joules per atom. How would you change that? How many atoms are in there a mole? What's that conversion? That's Avogadro's number, right? Atoms in a mole. Okay, so let's do that. That would be 2.7304 times 10 to the 12th joules per mole. Let's set up our dimensional analysis so you don't multiply or divide when you should have been doing the other thing. All right, so I've got moles on the bottom, so you know what goes on the top, right? 1 mole. And what goes on the bottom, that would be, okay, 6.0, except we're going to use 2 because we're trying to be more accurate here. 2 times 10 to the 23rd atoms. Okay, and when we do that, we would get the binding energy per atom, okay, which is 4.534 times 10 to the minus 12th joules per atom. Great. Now, how do I get joules per nucleon? Okay, so I've got atoms right now. How am I going to change that to nucleons? How do you know how many nucleons there are?
How many protons?
Okay, protons, that's part of it. Nucleons, you remember what a nucleon is? It's protons and neutrons. Okay, so how am I going to find the number of protons and neutrons then? It's called, what is it called? The number of protons and neutrons? The mass number. That gives it to you. That is the number of nucleons, is it not? Okay, so the mass number is what we're talking about. So let's do another conversion. So this would be 4.534 times 10 to the minus 12th joules per atom. So if I've got atom on the bottom, I need to put 1 atom on the top of my dimensional analysis, and 1 atom, in this case of helium, because we're doing helium, is going to be 4 nucleons. Okay, and when you do that, divide that by the 4 nucleons. Let's see. Then it comes out to be what? The 1.13 times 10 to the minus 12th. 1.1335 times 10 to the minus 12th joules per nucleon. All right, so you see how we did that? Okay, so that's how we get the rest of these numbers. If you're just given the mass of the nucleus and how much a proton or neutron weighs, we should be able to do all the rest of these. Okay? So it's mostly just doing conversions, isn't it? A lot of conversions. E equals mc squared is not that complex. So it's just conversions, a little subtracting, right? Okay, same thing with iron. If you did the same thing with iron and the same thing with uranium-238. All right, that makes sense. So let's take a look at all of these. If we just did all the elements that way and said, hey, well, let's talk about what the binding energy is. If we're doing it per nucleon, that enables us to kind of compare them. So we were to compare them. Now remember we said the more energy, binding energy, what does that tell you about the nucleus? It's more what? It's more stable, right? And everything kind of goes towards stability. So the most stable nucleons, or atoms then, would be the ones with the highest binding energy, wouldn't it? Okay, so let's take a look at that. So if we plotted all of these, then we can look and say, wow, the ones at the highest part of the curve there, that's going to be the most stable. So the most stable are going to be in this range here with our atoms, our nuclei right there. That's the most stable. So if you're bigger and you're not as stable and you want to go towards stability, then you're going to have to what? Split. Yeah, you're going to have to lose mass and split. That's what fission helps us do. It releases energy and we're getting to a more stable element. So that's why fission works. This kind of explains how come fission is the one that produces lots of energy, because we're trying to get to that stable area. Well, by the same token, well, what about a small one? You're trying to get to stability, right? So if you're small, how are you going to get to that? You'd have to gain, right? So that's where fusion works. So that's why fusion works for the smaller elements, fission works for the bigger elements. So that kind of explains how that happens and why that is. All right, so let's take a look at another one. Let's take a look at this one. All right, so here's an example. You've got the weight of the proton and the neutron and the weight of the nucleus. Now we need to do the same thing, so let's practice that. We want the mass defect, want the binding energy per atom, and the binding energy per nucleon. Okay, kind of like what we just did. All right, see if you can do that one.
Have more of an effect.
Yeah. 1.198 e to the minus 12. So does everybody get that?
Yes, ma'am.
Okay. Awesome. Woo, that's the end. Yay! We finished all the whole course. Okay, so the next thing we want to do is talk a little bit about what's going to be happening with, testing dates and all of that stuff.